All right, hello everyone. Welcome back. This is the third of 3 videos dealing with the straight poop. Just a quick review here of what I think the strategy is that you should have in mind. We go through this together and you go through this on your own as well at your leisure. Then that should adequately prepare you for the practice diploma exams that I've given you. And again, I think the best line of attack for those practice diploma exams is to pick one, sit down, phone put away, or better yet, in another room, TV off, computer off, no distractions, and you write the exam front to back, then you look at the answer key and see how you did. I don't think it's a good idea to do one question and then look at the answer key, do a second question and look at the answer key. Hopefully if you follow that kind of tiered approach to your prep, you should do well on the diploma exam. This final video is Unit 5, Unit 6, and Unit 7. Unit 5 is exponential and logarithmic functions, so let's get started. A basic type of exponential function is the graph that you're looking at right there. And it's an increasing exponential function of the form y equals some base raised to the x. It will be increasing if that base is greater than 1. So y equals 2 to the x is an increasing. Y equals 1.4 to the x is increasing. Functions of this form will have a y-intercept of 1, and something that I just realized I don't have on this, and I don't know if it's on your handout or not, is the x-axis is a horizontal asymptote. The thing to remember, though, is that if the base is greater than 1, it will be an increasing exponential function. If we take our template of y equals a f of bracket b bracket x minus h n bracket plus k, which is on our formula sheet, and apply it to y equals c to the x, we get that beast that you're looking at. And I guess since you know what y equals c to the x looks like, you ought to be able to tell me what the properties of any graphs are that are transformations of that y equals c to the x. Decreasing exponential functions look like that. Again, it's of the form y equals some number raised to the x, but in order for this to be a decreasing function, the value of that base has to be between 0 and 1. And again, there's a y-intercept of 1, and I haven't drawn it in, but the x-axis is a horizontal asymptote. Again, if you apply, and that's key, decreasing automatically means the base is between 0 and 1. If you apply our template for transformations to y equals c to the x, you get that, and the same thing. You know what the graph looks like in the right-hand side of your screen, so you ought to be able to tell me what any transformation of that graph looks like and what the properties of the transformation are. So this is the graphic that I've given you in your handouts, not in the straight poop handout, but in your unit handout. It's a good way to visualize that the base can be any number between 0 and 1, or it can be any number bigger than 1, but it can't be negative, and it can't be 0, and it can't be 1. If it's between 0 and 1, it's a decreasing function, and if it's bigger than 1, the function is increasing. Exponential growth and decay. For exponential growth and decay, this is the formula that you need to use. This is on your formula sheet. You need to know, and I'm going to present these in a different order, you need to know that y is a quantity that's growing or decaying, and t is the time that's elapsed. And I'm indicating those two things first because I think it's important for you to understand those are the variables. Those are like our y and our x, except we use y and t. A, b, and p are parameters. What a is the initial amount of whatever is growing or decaying. B is the factor by which things change regularly. It's what the quantity is being multiplied by at regular intervals. And p is the length of time in between applications of that factor. How long it takes until that factor gets applied again. To give you some illustrations here, I guess we'll talk about the two shapes first of all. It can look like this or this. The graph on the left is increasing, the graph on the right is decreasing, but we use these words now instead. We say that the graph on the left shows growth, the graph on the right shows decay. So as illustrations of what to put for B and P, if you have a science question, which you can see in this course often, where you're told the half-life is 34 years, that means that every 34 years, things get cut in half. So if they get cut in half, then that means B is 0.5. And if it happens every 34 years, that means the period is 34 years. Another example, if the population of something, maybe it's bacteria, maybe it's mice, maybe it's population of London, I don't know, it doesn't matter. If the population grows by 4% every 1 year, growth by 4% means B is 1.04, because 4% is being added to 100% to get 104%, which is 1.04 in decimal form. And P is a year because it happens every year. If I tell you that the value of something declines, which means decreases by 12% every 6 months, then P is going to be 0.88. And just mull that around in your head for a second. How is losing 12% the same as multiplying by 0.88? Well, if I take 100% and subtract 12%, I get 88%, and 88% in decimal is 0.88. The fact that it happens every 6 months means we could use for P 6 months or 0.5 years. I'm a year kind of thinker. I like to use all of my times in years. Interest is compounded at 8% per year quarterly. That means you only get 2% every quarter, so it's 1.02, and the period is 0.25 years. Be careful when you solve problems like this with compound interest, because if you're finding a time and you get for a time for an answer to a problem in the bottom statement, 8% quarterly, you get a time of 1.77 years. You must round to 2 years because interest is earned every quarter of a year. Interest is earned at 1 year, 1.25, 1.5, 1.75, 1.2. So you're always rounding up to the next compounding period. When we take a look at this graphic that is in your notes in the unit handout, we can now say, well, if it's a decreasing function, that's exponential decay, and if it's increasing, that's exponential growth. Okay, on to logarithms. We start off with the idea that the inverse of an exponential function is what we call a logarithmic function. So if I have y equals 3 to the x, which is called an exponential function, and I say, what is the inverse? The inverse is found by swapping x and y to get x equals 3 to the y, and these are inverses of each other. Okay, let's just forget about logarithms for a second. Those are inverses of each other. But we like to write inverses in terms of y. We want to write y equals. And when you take a look at that x equals 3 to the y and say, well, how do I write it as y? It turns out there's a new invention in the math field. It's not new currently, but when people studied math, they said, well, how are we going to rewrite that for y? They said, well, we have to invent a new notation. And the notation that we use is that x equals 3 to the y is the same as y equals log base 3 of x. So these things are the same. And you ought to be able to convert back and forth between an exponential expression like x equals 3 to the y and a logarithmic expression like y equals log base 3 of x. But they're the same as each other. What that means is that x equals 3 to the y, which is the inverse of y equals 3 to the x, that x equals 3 to the y is the same as y equals log base 3 of x. And this goes back to the beginning where I said the inverse of an exponential function is a logarithmic function. What I have highlighted in blue and what I have highlighted in yellow, 2 lines below, those are inverses of each other. Y equals 3 to the x, which is that blue graph, and y equals log base 3, which is the red graph, these two graphs are inverses of each other. Now, what about the graphs of logarithmic functions? You're expected to know what the graph of y equals log base c of x looks like if c is greater than 1. And it looks like that. This happens to be log base 2 of x. And since you are expected to know what that looks like, and there is a vertical asymptote on the y-axis, you're expected to be able to tell me, or a marker on a diploma exam, and you're expected to be able to answer exam questions that test your knowledge of what a transformed version of that graph would look like. Whether it's where the vertical asymptote's going to be, which direction it curves, all of that. So knowing the properties of the above graph allows you to find the properties of any transformations of it. Now, you're also expected to know what this graph looks like if the base is between 0 and 1. And it looks like this. According to the diploma exam and the standards documents that I see, you are not expected to know the properties of transformations of this graph. But I have seen questions on diploma exams that if you did understand this, it would be helpful for you. So knowing the properties of the above graph will allow you to find properties of the transformations of it, but chances are you're not going to need to use this on the diploma exam. Laws of logarithms. We have the product law, we have the quotient law, and we have the power law. That power law, notice that the power of m to the n, that exponent on the power, on the base of m to create the power, is part of the argument. That's what allows you to move that exponent in front. Basically, these rules can be used to rewrite equivalent logarithmic expressions, to simplify logarithmic expressions, and to solve some logarithmic equations, or to solve some exponential equations. Remember that I've shown you this shortcut that for the product rule, if you have a logarithm that's negative, you divide by that argument when you put it all together as a single logarithm. But if the logarithm is positive, you multiply by that argument. The bases have to be the same when you apply these rules. So when you take a look at the product law, log base b of m times n is log base b of m plus log base b of n. If those two bases are different, you cannot apply these rules. Solving exponential equations. This is something that traditionally you see on a diploma exam, on a written component. If you can rewrite each side of the equation using a common base. Now remember, the purpose of these videos in this handout is not for me to do problems with you. You can look back in the lesson dealing with solving exponential equations. When we first learned this, we had bases in the equations like 81 and 27, and it was possible to rewrite each part of the equation with base 3, for example. The basic idea here is that if you can simplify an exponential equation so that each side is the same base, and you simply have b to one thing equals b to another thing, then those two exponents are equal. If the bases are not compatible, you have a base of, say, 3 in one term and a base of 4 in another, then at some point you're going to have to take the logarithm of both sides so that you can use the power law, which moves the exponents in front, and that will allow you to solve the equation. I'm telling you that everything on the screen right now is potentially a written response question where you have one part maybe for 2 marks and one part for 3 marks, and you have these two types of exponential equations. There are also logarithmic equations that we need to know how to solve. There's 2 basic strategies. There can be more, but if you can rearrange it, or arrange it rather, so that each side contains a single logarithm that's the same base logarithm, then you can do the same strategy that you did with an exponential equation with the same base. Namely, if you have log base b of a thing equals log base b of another thing, those two things have to be equal. On the other hand, maybe you have a logarithm equals a non-logarithm, in which case you rewrite that logarithm in exponential form to solve it. And again, the purpose here is not for me to go over problems in this video. The purpose is to remind you of everything that you're expected to know how to do. So it's at this point in time, if you wanted to, actually, you could pause the video, go back and look at some of the problems that we've done in our lessons dealing with solving exponential and logarithmic equations and practice them. Always, though, with logarithmic equations, check for extraneous roots. Extraneous roots for logarithmic equations are any values of the variable that you find that result in you taking a logarithm of a negative number. That doesn't mean you can't have negative solutions. It just means that the arguments in the equation can't be negative. Unit 6 is rational functions and function operations. We started off by analyzing rational functions. Rational functions are functions that contain polynomials over polynomials, and non-permissible values of rational expressions, or rational functions, happen when you divide by 0. So, little tiny example here, if you had x minus 2 as a factor in the denominator, then x is not allowed to be 2. A non-permissible value of x being 2 exists. The non-permissible value in a rational function may turn out to produce what's called a vertical asymptote, or it may turn out to produce what's called a point of discontinuity, or a hole. If the factor that produces the non-permissible value does not cancel with an identical factor on the top, it survives, then you're going to have a vertical asymptote there. If, and by the way, that should be v. I think on your handout it says something else. If the factor that has the non-permissible value does cancel, and again, I think there's a typo in your handout. If that factor does cancel with an identical factor, then you will produce a hole or a point of discontinuity. If there is a hole and you want to find the y coordinate, then take the non-permissible value that's the x coordinate at that hole and put it back into the expression after you've canceled that factor and see what you get. That's going to be the value that the function will approach as x approaches the non-permissible value. In other words, it will be the y coordinate of the hole. And the final thing is if you have a factor in the numerator that doesn't cancel, it's responsible for an x-intercept. So if after canceling you had x plus 3 in the numerator, x equals negative 3 would be an x-intercept. Horizontal asymptotes. Many rational functions have a horizontal asymptote. It will have an equation of y equals some number. That number is the value that y approaches when x gets really large. So, I mean, if you wanted to find out if there's a horizontal asymptote, you could put in a very large number for x and see what y is getting closer to. This is only going to happen if the degree in the numerator is the same or smaller than the degree in the denominator. So if the degree in the numerator is higher, you will not have a horizontal asymptote. There's some tricks here. And it's that if the degree in the numerator and the denominator are the same, you simply divide the coefficients to get the location of the horizontal asymptote. If the degree in the numerator is smaller, then it will always be the case that the x-axis is a horizontal asymptote. And as I said, if the degree in the top is larger, you will not get a horizontal asymptote. Function operations. Well, first of all, you need to know that f plus g in brackets of x means f of x plus g of x. And that simply means that the new function is found by adding the two functions. When you add functions, just like adding numbers, the order is unimportant. You need to know that f minus g in brackets of x means f of x minus g of x. It just means that you subtract the corresponding functions. But of course, the order does matter. So f of x minus g of x is not the same as g of x minus f of x. We have this domain rule that says if you want to know the domain of the sum of two functions or the difference of two functions, it's the domain that they have in common. And we've talked about this numerous times in class. You cannot add things together unless they both exist. So if one of the functions doesn't exist, say to the left of the y-axis, then the sum of the functions can't exist to the left of the y-axis. The sum or the difference of the functions will only exist wherever they both exist, wherever their domains overlap. There is no tidy range rule. You have to find the new function and look at the new function and or the graph of the new function to determine the range. Continuing with sums and differences, the only difference here in what I'm showing you is that I have f plus g not of x but of a, and a is just some number. It's a specific x coordinate. And this means that you're going to take f of a plus g of a, but f of a is a y coordinate on f when x is a. G of a is the y coordinate on g when x is a. So what I'm telling you is you're adding the y coordinates. And the order doesn't matter because when you add numbers, order doesn't matter. What about f minus g quantity of a? Well, that means f of a minus g of a. Well, that means that you're going to subtract the two y coordinates. You're going to take the y coordinate on f at x equals a minus the y coordinate on g at x equals a. And of course, when you subtract, order matters. So f of a minus g of a is not the same as g of a minus f of a. These two y values that you were going to add or subtract may be found by looking at equations of the functions, if you're given them. They may be found by looking at the graphs of the functions, if you're given them. They may be found by a list of ordered pairs or a table of values, if you're given them. And you might be given the equation for f and the graph of g. But remember, it's y coordinates that you're after. Products and quotients, well, again, this first part is just about notation. F times g of x means f times g of x. It means f of x times g of x. And we use a solid dot to indicate multiplication in those brackets. It means that you're multiplying the two functions to get the new function. And order doesn't matter because when you multiply things, order doesn't matter. F over g, quantity of x, means f of x over g of x, or f of x divided by g of x. And that just means the new function is found by dividing. And of course, order matters because order matters when you divide things. I don't mean to be flippant there. Order matters when you divide things. 10 divided by 2 is 5. 2 divided by 10 is not 5, it's 0.2. The domain of the resulting function for each of the following follows the same domain rule that we use for addition and subtraction, except that when you divide, you're not allowed to divide by 0. So any place in f over g of x, any place g of x is 0, is non-permissible and is removed from the domain. Once again, though, the range can only be found by looking at determining the new function and graphing it. Continuing on with products and quotients, let's do the same thing we did with sums and differences. The only difference here is a is a specific value. All this means is you're multiplying the y coordinates. And again, order of multiplication is not an important feature in mathematics. F over g of a means f of a over g of a. F of a is simply a y coordinate, so is g of a. So this is found by dividing the two y coordinates. You take the y coordinate on f at x equals a, divided by the y coordinate on g at x equals a, to get f of a over g of a. And again, order matters because the order of division is important. Where do you get these y coordinates from? Whether you're adding or subtracting or multiplying or dividing, again, you can get them from graphs of equations, you can get them from tables of values, you can get them from the actual equations themselves or lists of ordered pairs, a lot of different ways that they might be presented. All right, moving on now to what are called composite functions. This is read as f of g of x. Notice that that dot in between f and g is actually a circle. That's not to be confused with f times g. And what f of g of x means is f of g of x. Specifically, it means that g of x is going to be put in to the function f every place there's an x. The domain is found by looking at the resulting function before it is simplified. This is really important. To illustrate this idea, if I had f of x equals 2x squared minus 3 and g of x equals the square root of x minus 1, that means f of g of x means f of g of x, and it means that g of x is going to go in for x in f of x. To illustrate this, I'm just going to draw that in. It means that this thing here is going to go right in there, and then we're going to end up squaring it. Right? So we're going to get 2 times the square root of x minus 1 quantity squared minus 3. Now at this point in time, when we square the square root of x minus 1, we'll just get x minus 1. But the domain is still restricted by that radical. X minus 1 must be greater than or equal to 0, which means x has to be greater than or equal to 1, even though if we were to simplify that, it would simplify to 2x minus 5. The reason for that is when you evaluate certain points on this graph of f of g of x, you put the number into g of x first. And when you put the number into g of x first, there's a restriction on the number that you can use. You can't put negative 8 in for x in g of x, which means negative 8 is excluded before we even get to the next stage of substituting the result in for x in f. So that bold section there is important. In fact, that's probably true for anything, rational functions, any functions. The domain is always found by looking at the resulting function before it's simplified. Moving on, more specifically, f of g of a means f of g of a, and a is a specific value of x. It means you put the value of a in for x in the function, and then whatever you get coming out of the function g, you put in for x in the function f. And whatever you get coming out of that is the answer. So to illustrate that, this is kind of how we do it in class. A is run through g to get an output which is called g of a. G of a is run through f to get a new output which is f of g of a. So that g of a in the middle of your screen is both a y coordinate on g, because it's coming out of g, and an x coordinate of f. If you're using graphs, you would find the y coordinate on the graph of g using an x value of a. Then you would take that y coordinate and it now becomes an x value for the graph of f. So you would then find the output, which is the new y coordinate. We've done lots of these examples. I think you guys are pretty solid on this idea. Just be careful that you get the order right. We've talked about this a little bit already, but when working with function operations, whether you're adding or subtracting or multiplying or dividing, remember that it's y coordinates that are being combined. So you look on the graph at a specific value of x. Maybe you go to x equals 2, and you look at the y coordinates at x equals 2. And those are the numbers that you're going to add or subtract or multiply or divide. I don't think too many people can simply look at two graphs that are being added or subtracted or multiplied or divided and know what the resulting graph is going to look like. I think you need to add or subtract or multiply or divide the y coordinates at a certain value of x and plot the new point at that value of x, and then move to a new value of x and repeat the procedure, and do that enough that you start to get a picture of what it looks like. Included in here, and this includes compositions as well as operations, I think you should be able to handle situations like I have at the bottom of the screen. Namely, it doesn't just have to be two functions, or it doesn't just have to be two operations or two compositions. It can be multiple layered operations or compositions. Or it can be a composition divided by an operation. Or it can be a composition minus a composition. Could conceivably be. On to the final unit, Unit 7, Perms, Coms, and the Binomial Theorem. As I said, I think at the beginning of this video, I think I'm going to go a little bit quicker here because this is more recent in our memory. So we start off with the fundamental counting principle, which basically says if you have multiple tasks to do, Bobby Bear's got to put on a pair of pants and a shirt, then the number of ways he can do that is found by taking the number of pairs of pants times the number of shirts. And the way to illustrate this is basically the word and means multiply. And there could be more than two stages. You know, Bobby Bear might have a whole bunch of shirts to choose, a whole bunch of pants to choose from. He's got 3 belts and 4 pairs of shoes. And he has 5 hats. How many ways can he get dressed if he's going to wear one of everything? Well, you'd take the number of shirts times the number of pairs of pants times the number of belts times the number of pairs of shoes times the number of hats. One other idea when used in solving these problems is the idea that or means plus. This is not the fundamental counting principle, it's just another idea. If, as I said in class, kind of jokingly, if Bobby Bear has 3 shirts and 2 pairs of pants, and he's a little confused one morning, and he thinks he just has to wear a shirt or a pair of pants, then the number of outfits is 5. He can put on the blue shirt, the red shirt, or the green shirt, or he can put on the gold pants or the yellow pants. So or means add. When solving problems, make sure you deal with restrictions first. We've gone through enough of these for you to know that. The most difficult thing in this unit, of course, is trying to figure out how to interpret what the question is saying into a fundamental counting principle situation. Sometimes it's a permutation, sometimes it's a combination. Again, I mentioned that because some people mistakenly believe that the fundamental counting principle is about permutations because that's where it's presented in your textbook. And it's about permutations or combinations. Factorial notation, we've talked about this numerous times in the previous week. The main reason you need to know what n factorial is in terms of a product of factors involving n is because if you had something like n factorial over n minus 2 factorial, that n minus 2 factorial is contained in the n factorial, and you have numerous examples that we've done in this lesson and in the review handout that involve the simplification of something like n factorial over n minus 2 factorial. By the way, n factorial over n minus 2 factorial simplifies to n times n minus 1. By definition, 0 factorial is 1. A permutation is different than a combination because a permutation order is important. Things like lining up people for a photo, or the number of different ways horses can finish a race, or the number of different ways I can eat a plate of 3 chocolate chip cookies, 3 coconut cookies, and 2 oatmeal cookies. The number of permutations of R items taken out of a group of n is written as NPR, and it can be found using n factorial over n minus r factorial. I think under most circumstances you wouldn't actually use that formula to solve these problems. You would just use your calculator, or you would use the fundamental counting principle if you could. Permutations with identical items. I hate that we say with repetitions. That's not what we mean. We mean with identical items. So if I have n items that I'm going to arrange, say 10 books, and I want to put them on a shelf, normally I would just say there are 10 factorial ways of arranging them. But if some of the books are identical, then I have to divide by that factorial of the number that are identical. So, for example, if I said, how many ways can you arrange all of the letters of the word tooth? There are 5 letters, so you would say it's 5 factorial. But then you would divide by 2 factorial because there's 2 t's. And you would also divide by 2 factorial because there's 2 o's. Another example would be arranging 11 cars in a row where 5 are identical blue cars and 6 are identical red cars. It would be 11 factorial over 5 factorial and also over 6 factorial. Another example, there are a number of ways to eat 4 chocolate chip cookies and 3 coconut cookies, assuming I eat them one after the other. Would be 7 factorial over 4 factorial and also over 3 factorial. We use this idea to find numbers of pathways. We've kind of done this one to death, but let's go through it one more time. If I want to know how many ways I can go from A to B, always moving closer, I must make 6 moves to the right. If you count those blocks, I have to move to the right 6 times, and I have to move down 4 times. And I don't have to move to the right in my first 6 moves. I can move to the right a couple of times and then down and then to the right again and continue in that fashion. My point is that each time I arrange these 10 letters, I'm going to get a unique pathway. So the question is, how many ways can I arrange those letters? Well, it's 10 factorial, but I have to divide by 6 factorial, 4 factorial. And that would be the answer to this question. Don't quote me on this, but I think it's 210. You can check it on your calculator. I'm pretty sure it's 210. If I said to you with the same grid, how many ways can I get from A to B through C? Essentially what you do is you look at the grid, and you need to look at the screen right now for the next few seconds as I say this. You look at the grid and you say, if I have to go through C, I cannot be in any of those places, so they're gone. If I find myself in the place to the left and below C, that's wrong because I would have to move back up, and I'm not allowed to move back up. I have to move to the right and down. Again, in your handout, I believe I've got the letters wrong there, so the highlighted portion is correct. From A to C, I have to make 4 moves, right, right, down, down, but I have 2 rights and 2 downs. I have to make 6 moves from C to B, right, 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 down, down. Of course, I have to move from A to C and C to B, which means I multiply those, and that would be the answer to that question. And I believe that answer is 90. Now, what if I said, how many ways are there to get from A to B not through C? It can only be found in one way. You have to take the total number of pathways and subtract the number that go through C. Just to remind you, the total number of pathways is the number at the bottom of the page. That's the total number of ways to go from A to B. And some of those you'll be going through C, and some you won't. So if I subtract from that this number, which is the number through C, I'm going to get the number that do not go through C. And again, I think 10 factorial over 6 factorial, 4 factorial is 210, I'm pretty sure. 4 factorial over 2 factorial times 6 factorial over 4 factorial, 2 factorial, I know is 90. I think the answer here when you subtract them is 120. Combinations. Well, a combination differs from a permutation because order is unimportant. So selecting students to go on a trip, dealing cards in a poker hand, flavors of an ice cream, flavors for a topping rather that you're going to put on an ice cream. These are all combinations. The number of combinations also has a formula. We write it as NCR, and it's equal to n factorial over n minus r factorial times r factorial also on the bottom. So that r factorial on the bottom is new. It's not there with a permutation, but with a combination we have that extra r factorial. NCR can also be written that way, and that just means if you ever see two numbers stacked on top of each other in brackets, it's a combination. There's no equivalent notation like that for permutations. And that takes us to the binomial theorem. The binomial theorem is used to expand a binomial of x plus y to the n. It's useful at times to note that if it's raised to the n, there's n plus 1 terms. You always get one more term in the expansion than the exponent on the binomial. The general term, which is how we find each term in the expansion, is n choose k, x to the n minus k, y to the k. N is the exponent on the binomial, and k is a number that's unique to each term. The first term uses k equals 0. The second term uses k equals 1. The third term uses k equals 2, etc. So basically you have to be able to work with that to find any term in an expansion of the binomial x plus y to the n. And I wouldn't recommend using Pascal's triangle, but if you get stuck, you can. You also have to be able to find missing pieces of a binomial by knowing a particular term. Every term in the expansion has the same x, the same y, and the same n. Their k's are different. If you want to find the first term, you have to use k equals 0. If you want to find the second, you have to use k equals 1. So the key number, the k value for each term, is 1 less than the term number. That's the end of Unit 7. I would remind you, however, throughout the semester, you've been given lots of review material from all 7 of the units, so you shouldn't limit yourself necessarily to the year review handouts. I hope that these videos have been helpful. I will see you all soon. In the meantime, take care, and we will talk to you later.